Okay, so convergence and divergence of sequences in series. So let's start with sequences first. An infinite sequence converges if all the terms after some place in the sequence become essentially indistinguishable from each other. Okay, so we start marching down the sequence and we get way out down the list, and the values start like honing in on a particular value and getting so close that you can't even tell, like you can't really tell the difference between them anymore. Okay, so a more formal mathematical definition of this is pick any degree of closeness. Pick any degree of closeness to this kind of value that you're honing in on. Meaning, make the difference as small as you want between values in your sequence and the limiting value. All right. Eventually, the sequence will get within that degree of closeness and never depart again from that. Okay, but that works for any degree of closeness, right? So you think, okay, I want my values of my sequence to be within 0.0001. 0.0001 of this final value to where it's heading. All right, so that's the difference. So there has to be somewhere in the sequence where the difference between your values in the sequence and your kind of limiting value, the difference is less than this and will always be less than that. But then this works for any degree of closeness. So then you can take it 1 times 10 to the minus 10th. Like 0.10 zeros and a 1. So somewhere in the sequence, it has to get that close and then always be that close after that. But then you can make the closeness, the closeness factor smaller, as small as you want. And that sequence has to get there. That's what we mean by convergence. Okay? So in other words, the limit of a convergence sequence, so I'll write that sequence in function form, right? There's function form. As I gets very big, the limit is L. And the meaning of this is what I just explained to you. Pick any degree of closeness to L. Values of the sequence I will get within that degree of closeness and then never leave it. But then pick another smaller degree of closeness and take it out further down the sequence. And you'll get within that degree of closeness. If this doesn't happen, then we say the sequence diverges. So there's 2 main ways that a sequence can diverge. Either the values just keep getting bigger and bigger and bigger, either bigger and bigger, negative or positive, or the values just keep jumping around. They're not honing in and getting particularly close to some limiting value. All right, so example. So here was the very first sequence we looked at. The odd numbers. It's 2i minus 1, right? 2i minus 1 was our formula for that sequence. Convergent or divergent sequence? Divergent. These numbers just keep getting larger and larger and larger. This list of numbers is not honing in on a particular value, getting really close to a particular value. All right, I think this was one of the next ones we did. So negative 1 to the I, 2i plus 1 over I plus 1 squared. Yeah, this was like the second example we did. How about this one? So notice what's happening. The numerator is getting big, but how does the denominator get big compared to the numerator? Yeah, so it's squaring, right? So if you remember from pre-calculus, you had these rational functions. And you looked at end behavior, like looking for a horizontal asymptote, right? Remember that? So this is kind of the same thing here. We've got a rational function, 2i plus 1 over I squared. And what did we look at to determine the end behavior, or if there was a horizontal asymptote of those rational functions? Remember what we did? Or what you did? Do you remember looking at the leading term of the numerator and the leading term of the denominator? What's the leading term of the numerator? 2i. What's the leading term of the denominator? I squared. If you multiplied that out, you'd have I squared. So this is essentially 2 over I. And when I gets really, really big, the leading term is what governs. This plus 1 and the rest of these terms down here kind of fade away. They become kind of like 0 compared to the leading term. So this whole sequence becomes like 2 over I. So if this whole sequence is like 2 over I and I gets really, really big, does this converge on a value or diverge? Converges to 0, right? So I is allowed to get infinitely large. That fraction will get as close to 0 as you want it to, right? Pick any degree of closeness to 0. Eventually, the sequence will satisfy that degree of closeness. Now pick a smaller degree of closeness. Eventually, it'll satisfy that degree of closeness. So it will get to any degree of closeness that you want. That sequence, the values will get close to 0. So that converges to 0. How about this? This was the next one we did. So this is 2 to the I minus 1 over I. So we got 4 thirds, 2, 16 fifths, 16 thirds, 64 sevenths. What are those values doing? So this is like 1.3. This is like 3.2. 16 thirds is 5.3. 64 sevenths is 8 point something. 9 point something. What about this? Diverging, right? 2 to the I is going to get a lot bigger than I. And as 2 to the I gets bigger, much, much bigger than I, this whole fraction blows up, right? Diverges. So as you march down the list, do the terms get closer and closer to each other, right? So close to each other that there's a limiting value L. Then you have a convergent sequence. Otherwise, any other situation, it blows up positive infinity, it blows up to negative infinity, or it jumps around, just keeps jumping around, diverges. Questions on that? Yeah, please.
So even in B, even though it switches between positive and negative,
Okay.
it's still convergent.
Yes, a good question. All right, so if they were all positive, you'd be fine with that, right? So in this case, if we think about, so values of the sequence here, B sub I is on the y-axis and values of I on the x-axis. So what are we going to see? It's going to be like this. So they get closer to 0, but then they flip back and forth, this. So even with every other one being negative, do we have this like getting as close as you want to 0 still? Yeah. You see that? Yeah. Other questions? Yeah, so alternating, if you're alternating, it's only 0 though, right? So if it was alternating, but this converged to something like 3, and then it was alternating, then it would be divergent, because you end up like 3, negative 3, 3, negative 3. That would diverge. So not just because this converges, the only way that the alternating will also converge is if that converges to 0. Okay. So let's talk about some common forms of sequences that we have to kind of be on the lookout for. The first one's called a P sequence. I have toddlers. We know all about the P sequence. So 1 over I to the P. This is a P sequence. So your index is the base. And then this is some constant for that particular sequence. So P is some constant for a particular sequence, and then I, your base, is your index. 1, 2, 3, 4. That's I. So we're asking for what values of P does I to the P get really big and thus the reciprocal get really small? So we're saying for what values of P does a P sequence converge to 0? So let's see here. So here's 3 examples. One over I cubed. So let's write out the first 4 terms. What are the first 4 terms of 1 over I cubed? 1 and what? 1/8, 1/27, etc. Converge or not? Yes, converges to 0. All right, 1 over 1 I to the 1/2. What's 1/2 power? Square root, right? So this would be 1 comma what? 1 over radical 2. 1 over radical 3. 1/2. 1 over radical 5. What about this? So what does square root, what's the function square root look like? Does it ever flatten out, square root? Or the values just keep getting larger and larger and larger, infinitely large? Square root. You never run out of i's, right? You never run out of i's. So any denominator that you want, 1 over any denominator, all you have to do is go out to I squared, the I squared term, and you get 1 over that denominator. So, does this converge or not? Yes, converges to 0. So even though it's square root, the square root function just keeps increasing, right? Pick any value of y in the square root function, you can eventually find an x that'll get you that y. This just keeps getting, it does not flatten out. Therefore, converges to 0. All right, what about 1 over I to the negative 2? Why? Right, so this is 1 over I to the minus 2 is really the same sequence as I squared. Clearly that's going to diverge, right? Those are just going to get big. Okay, so converges for positive values. What about fractions that are positive? Yeah, these are gonna get big much slower than, let's say, I cubed. I cubed gets big very fast, so that converges to 0 very fast. These numbers, square roots, they increase much less rapidly, but they keep increasing, and they never stop increasing. So you can get to any degree of closest to 0 that you want. But then the problem is if you have negatives. All right, so for what value of P do we have convergence? Positive, right? Any positive values. So this is just a very common form of a sequence that you have to be on the lookout for. And the thing you have to really remember is, for a particular P sequence, the P is that exponent. That exponent is fixed. And their index is the base of the denominator, right? So the base of the denominator is the one that changes. 1, 2, 3, 4. And the P value is the exponent, which is fixed for the entire sequence. And so P sequences converge to 0 when P is greater than 0. Okay? So here's how we could write that. 1 over I to the P converges to 0, arrow 0, as I gets very large if P is greater than 0. So that's how mathematically how we can write this conclusion of our P sequence. Okay, questions on that? Okay, so the next one's called a geometric sequence. A geometric sequence is of the form r to the I. R to the I. So now your index, what's different about this? Where's the index now? The exponent. Now the index is the exponent. R, the base, is this fixed value for the whole sequence. Make sure you... So there's a degree of memorization that you have to have first. And if you don't have that fact of like what each one of these are, then making sense of them is going to get confused. So make sure you got the memorization down. P sequence 1 over I to the P. Geometric sequence R to the I. Okay, so the question is, for what values of R does R to the I get really small, or get really big, or stay constant, or do something else? So it's like we investigate different values of R and make conclusions about what the sequence does. So let's look at these examples. And so maybe I'll have you write these down and write out the first 3 or 4 terms of each one. Meaning for I equals 1, I equals 2, I equals 3, and I equals 4. And then look at those sequences and try to make some conclusions about what would happen if I then got very large. Would it converge to some value or not? And I'll take attendance. This first sequence is, what's this first sequence? First sequence is 1, 1, 1. Okay, what about this one? 2, 4, 8, 16. Okay, this first one. Convergent or not? Does it get as close as you want to a particular number? Yes. They're all 1s. So that converges to 1. Pick any degree of closeness to 1, and it'll always be within it, right? Because it is 1. How about this one? Divergent. What about this? 3/4, 9/16, 27/64. What do you think about that one? Converges to? Yeah, so what in these sequences, what's really going on with these sequences? How do you get from one to the next? How do you get in a geometric sequence, how do you get to the next term? Multiply by 3/4, right? Each one of the sequence has one more 3/4 in the one more 3/4 in the list of factors than the previous one. So it's like each one you get the next term of the sequence by multiplying by r. Times r, times r, times r. So in this case, you're always multiplying the previous value by 3/4. You keep taking 3/4 of your previous value. And that converges to 0. What about this one? Here, we're always taking -1/5 of your previous value. Converge or diverge? Converges to 0. What about this? Right, so this diverges badly because it's like 3, then -9, then 27, then -81, right? So it's like they're getting huge, and they're going big positive and negative every other one. So this is badly divergent, right? Okay, what about this? -1, +1, -1, +1. Does it converge to 0, the average of all those? No. The values need to get infinitely close to 0 for it to converge to 0. This does not do that. Right? You're not getting closeness to 0. You just keep jumping back and forth. So, for what values of r do you expect that this will converge to 0? So what, based on these examples, what do you think? R needs to be what kind of value for this thing to converge? Right, a fraction, less than 1, okay? So less than 1 yeah, right. So you're always taking some portion of what you had. If you always multiply and get some portion of what you had before, meaning r is a fraction between -1 and 1, then you'll keep, right, taking a fraction of it and keep reducing it. And that will get very, very close to 0. Now there's another trivial case. That's when r equals 1. But that's just kind of trivial, right? They just get all 1s. So when r is 1, it converges to 1, trivial case. When r is between -1 and 1, we get convergence to 0. Any other r value, it spirals out, right? Either out to positive infinity or positive and negative infinity. So let's summarize that. So this sequence goes to 0 as I goes to infinity if what? R is between -1 and 1. And then you got this trivial case. R sub I will converge to 1 if r equals 1. But that's trivial just because you get the sequence of all 1s, right? So it's not really important. So this is the most important case here. Okay, so